All right, so we're going to talk about the conservation laws for the KDV. So, and these are really interesting because it turns out the KDV has an infinite number of conservation laws, and I'm going to show you why that's the case. But it was a really funny thing happened where I think people suspected there was something going on by the strange properties of it, but people actually discovered about 11 of these conservation laws before somebody actually proved there was an infinite number. So discovering the 11 would have been quite ingenious and quite tricky to work out. Okay, so the equation's written in conservation form if it looks like this. So that's what it looks like in conservation form. So just remember the KDV is given by d by dt of u plus 3d by dx of u squared, and this is how we write it, plus d by dx of u, the third derivative of u equals 0. So we can write that in conservation form really easily, because this is d by dx of 3u squared plus the x derivative of u squared, second derivative of u. Alright, now we're assuming here that x goes between infinity and minus infinity, and we also are assuming that x of u is equal to, we're assuming that u goes to 0 as x goes to plus or minus infinity. Okay, so it's bounded and goes to 0, and that x of u is equal to x of 0 is equal to 0. Okay, I'm not sure those things are written down so clearly in the notes, those conditions. So what we do is conservation law is really simple. We integrate from minus infinity to infinity of the time derivative of t of u plus the x derivative of x of u dx. And that obviously is equal to 0. And then we break these up into the time derivative of the integral from minus infinity to infinity of t of u dx plus the integral from minus infinity to infinity of the x derivative of x of u dx. And an arrow there. So this is the time derivative of minus infinity to infinity t of u dx, and of course we can integrate this. Okay, plus it's x of u evaluated at minus infinity and infinity, and which is equal to 0. So it must be the case that the integral from minus infinity to infinity of t of u dx is a constant, is conserved. So there's lots of conserved quantities in solutions of differential equations. So when you solve the equations of, Euler's equation, Newton's laws for gravity, you get conservation of angular momentum, that kind of thing here. So there's lots and lots of examples of conservation laws. So what we've got for the KDV, if we go back to our equation here in the green, it must be the case that the integral from minus infinity to infinity of u dx is equal to 0. Okay, so that's quantities conserved, it's always a constant. Okay, so that's one conservation law, and then we can manipulate the KDV and write it in different forms into different conservation laws. So I'll just show you how you do that. So we can derive another conservation law really easily by we can write d by dt of u squared plus, we can show that this is true. far from obvious why this is the case, why that is true for the KDV. So that is equal to 0. But we can show why that's true for the KDV by just expanding it. So we get 2u, the time derivative of u. So it's like we're multiply the KDV by 2u, right? And we're going to see that quite quickly when we work it out. And we just go through and expand this out. So this is going to be 12u squared dxu. This one here, if I differentiate it, I'm going to get 2 dxu dx squared u plus I'm going to get 2u dx cubed u. And then finally, I'm going to get another term here, which is minus 2 dxu dx squared u equals 0. Now, so this is, if you multiply the KDV by 2u, what you'd get, you wouldn't quite get this form, but there's a bit of a clever trick to put it into that form. That's where the trick comes in. That once you've seen it, it's obvious to show it. And the trick is to add and subtract this term here. These cancel. And now you can see that it's just the KDV multiplied by 2u. So it's 2u into the time derivative of u plus, this will be 6 u du dx, which is 3 dx of u squared. That's how we normally write the KDV. It could be written as 6u times dxu plus dx cubed u equals 0. Okay, brilliant. So we've manipulated that equation to that form. So it must be the case that, so that you can clearly see that that is equivalent to the KDV I've just multiplied by 2u, and I've rewritten it in this form. So we know, therefore, from the conservation rule that it's not this quantity here at all that's conserved. Okay, so this weird expression here means nothing. It's this quantity here that's conserved. So the integral from minus infinity to infinity of u squared du is also equal to a constant. So we've got, and you might imagine that the next one's going to be u cubed, and you're going to derive the next conservation law. I'm not going to give it to you, and you're going to work out what it is, but it isn't u cubed. It's not quite that simple. But there's another conservation law, okay, an infinite number of them.